Chapter 4.3, Logarithmic Functions. Remember, to find the inverse of a one-to-one function, you simply trade places with x and y. So the exponential function of this form y equals b to the x has an inverse function of this form, x equals b to the y. But we like our function solved for y. So another way we can write this is like this. Y is log with base b of x. Notice a logarithm is an exponent. A logarithm is an exponent. If the log with base b of x is y, y is the exponent that you put on a base of b to get x. I can even replace that word logarithm with exponent if I choose. Y is the exponent that goes on base b to get x. So the first thing we need to do is to be able to just convert back and forth between these two forms, back and forth. So let's try it right here. Log with base 3 of 1 over 81 equals -4. Okay, the exponent that you put on 3 to get 1 over 81 is -4. So I know this is my base because I want to always read that log with base 3. And since a logarithm is an exponent, this is my exponent. 3 to the -4 is 1 over 81. That's the exponential form. Logarithmic form, exponential form. 2 cubed equals 8 is obviously the exponential form. Okay. Log with base 2, there's my base for the exponent, right? And a logarithm is the exponent, so it has to equal the exponent. So I must be able to rewrite that as log with base 2 of 8 is 3. This number inside my logarithm is called the argument of the logarithm. Right? Log with base 2, the exponent that you put on 2 to give you 8 is 3. Here's the logarithmic form. Here's the exponential form. So to solve a logarithmic equation, we just simply change it to its exponential form, right? So if I have log with base x, base is x, and if a logarithm is an exponent, x to the 5th equals 1 over 32. Okay, and now this is an equation that we know how to solve. Take the 5th root of both sides so that we have x equals the 5th root of 1 is 1 and the 5th root of 32 is 2. Okay, x is log with base 3 of 1 over 81. So base 3, a logarithm is an exponent. And now use my ideas from the last section to solve this exponential equation. I want to see if I can make the bases the same, and indeed I can write 81 as 3 to the 4th power, right? 3 squared is 9, so 3 to the 4th is 81, but I need them to be in the same position. So negative exponents mean reciprocals. I can rewrite that as 3 to the -4. Once the bases are the same, then the exponents must be the same. To solve a logarithmic equation, simply change it to its exponential form. Logarithms and exponentials are inverses of each other, meaning they undo each other. So if I have a logarithm in my equation, the way to undo it is to change it to its exponential form. All right, If we want to investigate the graph of a logarithm, the key to remember, the key to graphing a logarithmic function is to change it to its exponential form, just like the key to solving a logarithmic equation. Second part of the key is you plug your basic points in for y. So here's the features of our graph. Let's graph one over here, and then we'll look at that. So let's say y equals, let's do like we did with the exponents, our most basic base. Y equals log with base 2 of x. So if I'm trying to graph this logarithm, then I'm going to change it to its exponential form. Log with base 2. A logarithm is an exponent. So 2 to the y equals x. Okay, now it looks just like our exponential form. And second key, plug in my values into the y field. If I put a negative 2 over here, I still wouldn't be able to solve that. 2 to what power is negative 2? But if I plug my values into my y, 2 to the negative 2, remember 2 to the negative 2 is 1 over 2 to the positive 2, so 1/4. 2 to the negative 1 is 1 over 2 to the positive 1, or 1/2. 2 to the 0, anything to the 0 power is 1. 2 to the 1 is 2. 2 squared is 4. And I have my points to plot. If x is 1/4, y is negative 2. When x is 1/2, y is negative 1. When x is 1, y is 0. When x is 2, y is 1. And when an x is 4, y is 2. So plugging these values in, I have another shape to add to my list, the shape of a logarithm. Notice its features. Just like the exponential always contained the point 0, 1 and 1a, this one has the point 1, 0. Everything's just in the opposite place. It's the inverse of the exponential. So if an exponential has the point 0, 1, a logarithm has the point 1, 0. Instead of having a horizontal asymptote at y equals 0, it has a vertical asymptote at x equals 0. It's increasing if a is bigger than 1, increasing if a is bigger than 1, and it's decreasing if a is between 0 and 1. If it's a decreasing, if a is between 0 and 1, it's going to look like this. Sorry, it'll still go through that point. It's going to look like this, right? We'll look at one of those in just a minute. The domain is 0 to infinity. Remember, the domain of an exponential is negative infinity to infinity. And here the range is negative infinity to infinity, right? Negative infinity to infinity. Remember, inverse functions, everything is just in the opposite place. Now, don't forget, if I wanted to graph something like y equals, let's say, negative log with base 2 of x plus 3. I'm going to use my translations. So I've got to graph this basic function, or the basic points, right? Not really graphing that function, but I want to get my basic points. And then I'm going to take every one of those points, move it left 3, and flip it over the x-axis, or multiply the y value by negative 1. So left 3, 1, 2, 3, and negative 1 times negative 2 changes my y value to positive 2. Left 3, 1, 2, 3, negative 1 times negative 1 is positive 1. Left 3, 1, 2, 3, and negative 1 times 0 is still 0. Left 3, 1, 2, 3, but 1 times negative 1. And then left 3, 1, 2, 3, 2 times negative 1. Notice my vertical asymptote has been moved left 3. It's now at negative 3. All right, let's say we wanted to graph y equals log with base 1/3 of x. The key is change this to the exponential form. 1/3 to the y equals x, and plug your basic points into the y field. 1/3 to the negative 2. Remember, negative exponents mean reciprocals, so that's 3 to the positive 2, or 9. 1/3 to the negative 1 is 3 to the positive 1, or 3. 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. 1/3 squared is 1/9. And I wind up with, if x is 9, y is negative 2. If x is 3, y is negative 1. If x is 1, there's that same point that's always on. If x is 1/3, y is 1. If x is 1/9, y is 2. And here's my decreasing shape. Imagine I went through that point. Let's just make it a fat line. There we go. Okay, a decreasing shape when your base is between 0 and 1. All right, we've got some properties of logarithms that before the next period we really need to be familiar with these properties of logarithms. They come exactly from the properties of exponents, so that might help us remember when I add and when I subtract. If I'm multiplying two exponential numbers together, if you're multiplying two exponential numbers together, our property says you add the exponents, right? So if I'm multiplying my arguments, I add. Okay, if you are dividing two exponential numbers, you subtract your exponents. So here, if I'm dividing my argument, I separate them with a subtraction. If I have an exponent raised to an exponent, what do you do to those exponents? That's right, you multiply. Okay, so these properties allow me to either combine logarithms with the same base into one logarithm, or separate into individual logarithms with one single argument. Okay, then I have some basic properties down here. These three are really all basically the same, right? This is, what's the exponent? Let's start with this one. What's the exponent that you put on a to get a to the x? Obviously it's x. In other words, if these bases are the same, then these exponents have to be the same. If the bases are the same, the exponents have to be the same. So right here, my bases are the same, so obviously that equals 1 because these exponents have to be the same. Okay, and what's the exponent that you put on a to get 1? That's 0, right? Because a to the 0 is 1. This one not quite so easy to see, but again, if you get these bases the same, then these bits must be the same. So we really want to practice expanding and condensing. Here's when we're going to expand. All right. So I'm going to use these properties. I notice that I've got, first of all, recall that a fraction bar is as if there's invisible parentheses. So first of all, I've got two things being divided. I'm going to use this property right here to write this as log with base 5 of 5 square roots of 7 minus log with base 5 of 3. Now, this one I have one value as my argument, but over here I still have a couple of things, but they're being multiplied. So I can separate those two factors with a plus between them. Log with base 5 of 5 plus log with base 5 of square root of 7 minus log with base 5 of 3. Okay, so now I've got it separated. However, don't forget, a logarithm is an exponent. A logarithm is an exponent. A logarithm is an exponent. So is a radical. So if I have any radicals mixed in with my logarithms, I want to see everything written as an exponent. So I'm going to change this square root to its exponential form of 1/2. So now I recognize I've got this going on inside this logarithm's argument, and my property tells me I can just bring that exponent out to the front. So log with base 5 of 5 plus 1/2 log with base 5 of 7 minus log with base 5 of 3. Now, once I have my argument as one single value, I'm finished expanding. But just like anything else, we always have to make sure that we have completely simplified our logarithms. So I'm going to go by and look to see if I have any bases that are the same or can be made the same, just like in my exponentials. So if I have any basis that's the same, this will simplify to just whatever the exponent is through this property right here, right? So what's the exponent you put on 5 to get 5? Oh, it's 1. All of that will completely simplify to just 1. Now, 5 and 7, I can't write those as anything with the same base, nor 5 or 3. Notice I've expanded this logarithm into individual logarithms. Okay, likewise, if they're already expanded, I should be able to condense it into one logarithm, right, using these properties. But notice I can't have a number in front before I start condensing them into one. So my first step has to be to use this property to bring any number, any coefficient up as the exponent. So I'm going to rewrite this as log with base b of k to the 5th plus log with base b of m squared minus log with base b of a cubed. Okay, now I can combine these two that are being added if I simply multiply the argument. So I'd have log with base b of k to the 5th times m squared minus log with base b of a cubed. And now I can combine these two by dividing my argument to have log with base b of k to the 5th m squared over a cubed. And I have written these three individual logarithms into one logarithm. Don't forget to simplify any of your argument that's possible. Also, we might notice that, hey, these rules become very, very simple if I recognize, once I pull my exponents in, anything that is positive in front of the logarithm has a plus, those arguments are going to go in the numerator, and whatever I have with a minus is going to go in the denominator. So really I begin to get to be able to condense and expand these things in one step. In other words, I know this is going to be log with base 5 of 5 plus log with base 5 of square root of 7 because they're in the numerator, and then minus log with base 5 of 3. So after a couple of these, we can probably do them in one step. And I want to be really good before the next lesson at expanding and particularly condensing these logarithms. Okay, I think that gets this section. Let me know if you have questions.